Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my great pleasure to welcome Taylor Burke Kirkpatrick to visit us from Berkeley. Taylor has done a number of interesting work ranging from a diverse topic such as word alignment, summarization, and more recently on recognizing text from images. So and I have a number of us have been using things like, for example, like feature-rich EM that he has developed. So I'm very excited to have him here. And without further ado, here's Taylor.
Thanks. Hi. So this is joint work with Greg Durrett and Dan Klein, my advisor. And this talk is going to be about transcribing images of historical documents into text. So let me first just give an example of a historical document. I'll be mainly talking about documents from the printing press era. So here's an image of a document that was printed in 1775, and it's part of the proceedings of the Old Bailey Courthouse in London. Let me read just a little bit of it. Jacob Lazarus and his wife, the prisoner, were both together when I received them. I sold 11 pair of them for 3 guineas and delivered the remainder back to the prisoner. So researchers are interested in being able to do analysis on collections of documents that look a lot like this one. But in order to do many types of analysis, you first have to take these images and turn them into text. And so that's what this talk is about. So let's see what happens though when we take this particular historical document image and plug it into a modern off-the-shelf OCR system. And I'll use Google Tesseract as an example. So here's the transcription you get out of Google Tesseract. I've marked the errors in the transcription in red. And you can see there's a lot of errors. In fact, more than half of the words here are wrong. So that's a pretty terrible error rate. And that's weird because Google Tesseract is really good on modern documents. Most OCR systems are really good on modern documents. So next, to help explain why existing OCR systems perform so badly on historical documents, let me just quickly cartoon how a typical OCR system might work. So here's an image of some digitally typeset modern text. It reads the word modern. So the first thing an OCR system will often do is try to find a baseline for the text in the image. Once it's found the baseline, it will try to segment the pixels in the image into regions that correspond to individual characters. So Tesseract actually does that by identifying connected components. Okay, so once the image is segmented into characters, the system will then try to recognize each character segment individually. And that usually happens using some kind of supervised classifier that's trained on a single font or maybe a collection of fonts. So this kind of pipelined approach works really well on modern documents that are digitally typeset so that white space is really regular and where the font is known. But we've seen that kind of approach fails really badly on documents like this one. So now let me tell you the kind of the 3 primary aspects of historical documents that make them really hard for existing OCR. Well, the first problem is that the fonts in these documents are often unknown. So here's a rendering of the word positive in a historical document. We can try to line up a modern serif font with the first 2 characters. For this particular modern serif font, doesn't quite line up because the descender on the P isn't quite long enough. We'll try a couple more modern serif fonts. They don't line up. In fact, no modern font is going to perfectly line up with this image because the font used in the image is an ancestor of modern fonts. An extreme case of this problem of unknown font, you can see here with the use of the long S glyph. So we don't use this glyph anymore, so we don't even have a representation for it in modern fonts. Okay, a second problem that occurs in a lot of these printing press era documents has to do with the baseline of the text. So this example reads the death of the deceased, and you can see that the baseline of the text kind of wanders up and down as you go across the line. The glyphs kind of hop up and down. And so this actually has to do with the way that these documents were printed using the printing press. So humans take, templates, character templates, and align them using a mechanical baseline, and there's some slop in that mechanism. And as a result, you get this kind of noise in the baseline. Okay, a third problem has to do with inking levels and the fact that they vary across a lot of these documents. So this example reads, "Rode along in silence." And on the left of the example, the word "rode" is under-inked. It's so under-inked that the glyph for the character D is actually divided into two different connected components. On the right, there's a large degree of over-inking and bleeding ink, so much so that many of the glyphs have now come together into one big connected component. And this, again, is a result of how the document was printed. Maybe the ink was applied to the roller bar unevenly, or maybe pressure was applied unevenly when the document was printed. So here are portions of four different historical documents, one from 1725, 1823, 1875, and 1883. And you can see that the three problems that I mentioned are present in these four documents. And in fact, if you look, those three problems are present in pretty much all documents from the printing press era. So our approach is going to explicitly deal with each of those issues in turn. So the way we deal with the problem of unknown font is that we're going to learn the font in an unsupervised fashion from the document itself. We're going to deal with the noise that is a result of the printing process by jointly segmenting and recognizing, and doing that in a generative model that explicitly models the wandering baseline and also explicitly models the varying levels of ink across the document. So now I'll give you a high-level depiction of the generative model that we use. It's actually going to generate all the way down to the level of pixels. So first thing we do in the model is generate some text, character by character, and that comes from a language model. And now conditioned on that text, we're going to generate a bunch of typesetting information. And so this is going to look like a bunch of bounding boxes that tell you how the glyphs are going to be laid out. So specifically, the first thing we do for the character P is generate a left padding box. So this box is going to house the horizontal white space that you see before you actually get to the glyph for the character P. Then we'll generate a glyph bounding box for P, which will house the glyph for P and the vertical white space above and below it. And then a right padding box. And we'll do the same for R and the rest of the characters. So now we have a kind of layout. We're also going to generate for each of these glyph boxes a vertical offset for the glyph that goes in that box. And so this will actually specify the baseline of the text and allow it to wander as it goes across the document. And then finally, we'll generate an inking level, an overall level of ink, in each of these glyph boxes. And that similarly will allow us to model the wandering levels of ink across the document. Yeah?
What about the top? Do you allow the variation in the top margin?
So we're actually going to be learning the glyph shapes. And so once you've specified the baseline and you know the shape of the glyph in terms of its pixel layout, that then defines the top of the glyph as well. So that's enough to specify it. That'll become more clear as I'm going to dive into increasing levels of detail here. And okay, so then once we have all that typesetting information and the text conditioned on all that, we're going to actually start filling in pixels, and this will happen in the rendering model. So we're actually laying out the pixels for the glyphs. And then here we've generated an image of the text. Okay, so I'm going to name some of the random variables involved. I'll call the text E, and that's going to come from P of E, the language model. Sorry. And the typesetting information I'll call T, and that comes from the typesetting model, P of T given E. And then finally, the image itself, the actual grid of pixels, I'll call X. And that will come from the rendering model, P of X given E and T. And so the only observed random variable in our model is going to be X, the actual image itself. Both E and T are going to be latent random variables, and during learning, we'll marginalize them out, and when it comes time to do transcription, we'll fill them in with inference. Okay, so now I'm going to tell you more details about each of these three components in turn. Let me just say that probably kind of the first thing that popped into your head about what each of these components might look like is basically correct, with one exception. There's going to be a little extra level of complexity in the rendering model, and I'll tell you about it when we get there. All right, so first, let's talk about the language model. We're going to have a random variable E sub I corresponding to each character. All right? And these random variables will be distributed according to a Kneser-Nye smooth character 6-gram model that will train on a large corpus of external text data. So this is going to resolve a lot of the ambiguity when we're doing this in an unsupervised way. The fact that we have a strong language model trained on a bunch of data. Okay, so now let's talk about typesetting. Yeah. So we played with a couple different language models. You'll see them in a second. One is out of domain. It comes from GigaWord, and the other is in domain for some of the historical corpora that we looked at.
Okay, but it's not from that period of time. That's what I mean.
So the in domain one is from that period, and it was manually transcribed. There was a big curatorial effort that actually transcribed a bunch of these documents manually. And so we can use that to sort of see what the penalty is from using out-of-domain data. Okay, so I'll talk about the typesetting model, and we'll look at the typesetting process for the token at index I, and it works the same way for each token. So the character random variable at index I is E sub I, as we've seen, and let's say that that's an A. So the first thing we're going to do in the typesetting process is generate a random variable L sub I, which specifies the width of the left padding box. And L sub I is going to come from a multinomial. Then we'll generate a random variable G sub I, which is the width of the glyph box. And that's, again, going to come from a multinomial. And then finally, we'll generate the width of the right padding box, again, from a multinomial. And remember, the left padding box, horizontal white space, right padding box, horizontal white space, glyph box for the glyph and the vertical white space. And so these three multinomials are specific to the character type A. They govern the widths of tokens of type A and the distribution of horizontal white space around tokens of type A. And so that latter thing can capture effects like kerning. We're going to have similar multinomials for every character in the alphabet, and together all these multinomials are part of our parameterization of the font that we're going to learn in an unsupervised fashion.
So the box width you display from 1 to 30, are these the real parameters you use?
Oh, these pictures?
Between 1 and 30, the box width? Sorry,
The glyph box.
the glyph box width?
The glyph box width, yes.
Yes.
What?
Are you really using the parameter between 1 and 30?
Oh, here it depends on the height that we choose. So we downsample the resolution of the images so that each line is 30 pixels high. And then I believe that we cap the glyph box width at 30. It's the same as the height. So yeah, I think that's correct. That's actually what we use in the model, 1 to 30. And that's in terms of pixels. Yeah. Okay, so we're also going to generate the vertical offset, as I mentioned before, and that we'll call V sub I, but that's going to come from a global multinomial. And then finally, we'll generate the inking level for this glyph box, D sub I, again from a global multinomial. Okay, so now we're going to try to fill in the pixels for this particular glyph box token. And so far, we've generated the width of the box, the vertical offset of the glyph that's going in the box, and the inking level for printing that glyph in the box. And we're trying to fill in the grid of pixels, which is X. So there has to be something in our model that tells us the shape of the glyph for the character type A, because actually we're trying to print an A here because we're saying that this is an A. So that part of our model is going to be a grid of glyph-shaped parameters. And here I'm showing you a particular setting of the parameters that we learned in our model on some document. These glyph-shaped parameters are going to combine with the current glyph box width, the current vertical offset, and the current inking level to produce an intermediate grid of Bernoulli pixel probabilities that has the same dimensions as the particular glyph box token that we're trying to fill in. And once we've done that, we can just sample the pixel values in the glyph box from the corresponding Bernoullis. So the special thing about this approach is that our parameterization of glyph shape is actually independent of the particular width, offset, and inking level for the token we're trying to generate. And that means that we can fix the glyph shape parameters in the model and then vary the glyph box width to produce tokens with different widths. We can change the vertical offset to generate tokens with different baselines. And we can change the inking level to generate tokens with different levels of ink, all while keeping the shape of the glyph the same. And this is important because it means that when we're doing learning, when in the document we encounter an instance of an under-inked A, and then later in the document encounter an instance of an over-inked A, both of those sources of information can influence our notion of what the shape of an A glyph should look like. We don't have to have separate grids of parameters for under-inked A's and over-inked A's. And it turned out that this kind of shared parameterization that we're using was really important to getting unsupervised learning to work in this task, because after all, we're going to try to learn these glyph-shaped parameters unsupervised style. Okay, so here's where I'm going to go into a little extra level of detail. The key to getting this parameterization to work is how you define this function that maps the glyph-shaped parameters along with the width, offset, and inking level down to the intermediate grid. So I'll tell you about that process for a particular row of the glyph-shaped parameters, how it generates the corresponding row of the Bernoulli pixel probabilities. So I'll call the glyph-shaped parameter row phi and the Bernoulli pixel probability row theta. And first I'll tell you how we generate the leftmost Bernoulli pixel probability in the row. So in order to generate the leftmost guy, we interpolate the glyph-shaped parameter row phi with a vector of interpolation weights alpha that's shaped according to a Gaussian that's centered over to the left of the row of glyph-shaped parameters. Once we've done that, we just apply the logistic function, and that gives us the actual Bernoulli pixel probability. Now, to generate the remaining Bernoullis in this row, as we move along to the right, we just interpolate with different vectors alpha that are still shaped like Gaussians, but now are centered proportionally along the row. So this means that the Bernoulli pixel probability position j is generated by interpolating with a specific vector alpha sub j. And now our parameterization looks like this. Theta sub j is log proportional to the inner product of alpha sub j and phi. Now it turns out that we can get the various effects that I talked about earlier of varying width of tokens, varying the vertical offset, and varying the inking level by having these interpolation weights actually depend on the random variables g sub I, v sub I, and d sub I. All right, so I'm not going to, there's some more detail to be talked about there. I'm not going to talk about it right now. What I do want to say, though, before we move on to learning, is that you can actually view these interpolation weights like fixed feature functions in a locally normalized log linear model. And that means that when it comes time to learn the glyph-shaped parameters phi, we can actually use out-of-the-box unsupervised learning methods. So that's a nice property of the parameterization here.
So can I think of it as like you take your standard glyph shape and then just rescale them to whatever your current GI, VI, PI?
Yeah, so that's the effect that GI would have. So you'd have a specific, so for the position J, you'd have a specific set of alphas that would be used to map down the full width glyph shape parameters to a glyph box depending on G. So suppose you wanted to map down to a glyph box with width 10, you'd have a specific set of interpolation weights that would do that. And G would pick that out, but you define those ahead of time. Similarly, VI is just going to pick which row that you're pulling from. The trickiest thing here is DI. So it turns out that you can, because you're pushing this through a nonlinearity, by rescaling everything, by changing the interpolation weights, and by adding bias, you can kind of change things like contrast and darkness levels. And so you specify for each of the discrete settings of these random variables, you specify ahead of time the kinds of interpolation weights that you'll use. And then those are actually, they can be treated like feature functions, but they can actually do all these effects that we want using this single parameterization of shape phi, if that makes sense.
So those are like hand design.
Yeah. Yeah.
So another question is that in your VI, your baseline wandering and also your width, seems like from in your generative model, they are independent.
They are, yeah.
Okay.
But
it seems
there's
like,
reason to believe they shouldn't be, right?
Yeah, because
especially the baseline, which kind of, yeah.
Also inking, you can also imagine.
They should all be kind of slow varying. And even, I'll show you an example later where, because of three-dimensional warping, as you get near the bindings of books, there's actually slow varying in the change of the widths of the glyphs as well. So we don't explicitly model any of that, and it works really well. But we've thought about ways to extend it. We've seen a couple examples, a couple errors that we think it might actually lead to improvements, but there aren't a lot of errors that we think it would actually fix. But yeah, but I mean, it's an interesting, I mean, we can talk about it later. It's interesting how you might do it, because it gets, to just do it naively, you end up adding a lot of states to the semi-Markov model, and can get really slow, and this is already pretty slow. But you could think about using some kind of mean field approximation, because the offsets are basically independent of what's going on with the language model, and so it's an appropriate approximation. Okay, so I'll actually talk about learning. So we use EM to learn the font parameters, and so that again means learning both the multinomials governing the layout and the glyph shape parameters specifying glyph shape. And we initialize EM using font parameters that come from mixtures of modern fonts. So we just took all the fonts that appear on the Ubuntu distribution and mixed them down. And in order to get the expectations that we need for EM, we run the semi-Markov dynamic program, because the model itself is actually an instance of a hidden semi-Markov model. And then...
So the mixture, is it just uniform weight?
Yeah, uniform. The initialization mixture? Yeah, so there were... By hand, we identified some weird ones, like Comic Sans, or there's like a bunch of like Zaf Dingbats or whatever, and we just said those don't count. But the ones that actually look like text, we just uniformly put them together. And so to make this fast, we took a course-defined approach to inference. Okay, so now you know basically what the model looks like, and you know how we do learning and inference. Before I show you experiments, I just want to show you two examples of the system kind of in action. So here's a snippet of a document. It reads how the murderers came to. So if we train the model using EM on the entire page that this snippet came from, we learn some font parameters. And now with maximum likelihood inference, we can fill in the text random variables and get a transcription. So this is the actual output of our model, how the murders came to. We happen to get this one right. We can also do maximum likelihood inference on the typesetting random variables and use that to kind of peek into what the model is actually doing here. So here's a representation of the model's prediction about the typesetting random variables. The blue here corresponds to padding boxes and spaces, and the white boxes are the glyph boxes. So you can kind of see the layout. The glyphs that actually appear inside these white boxes are the Bernoulli pixel probabilities that the model chose to use to actually generate the pixels that it saw. Yeah?
So do you model space?
So the way we model space is we say it's a special type of glyph that has fixed parameters that are just white with some small probability of black for noisiness. Yeah. So we don't try to learn that. But so this means then that that spaces generate a glyph box, which is blank, and then 2 padding boxes, which is blank, which is kind of like there's an unidentifiability problem there, but it doesn't really cause problems.
How do you determine the width of a glyph box where the ink has been, whereas it's over inked? For example, M and RN, for example, would be.
Sorry, say again?
So M would be a wide glyph box, R and N would be 2 glyph boxes. But if you're given a...
So how would you distinguish
how do you
between those
distinguish
two?
between, if you're setting up the glyph box,
Yeah.
how do you distinguish between the case where...
So the language model.
The language model.
The language model would tell you, hopefully. Yeah. I mean, and some of the errors we get are because the language model was ambivalent about stuff like that, and you will see cases where, yeah.
Excuse me, I'm a bit confused. Can you tell me again your testing procedure? You see a document, and then you run through your model.
Yeah.
And then you get the global ink multinomial parameters, the global baseline parameters.
Right.
And then, so basically you do inference on the document.
So we run EM to get the
output
parameters,
is
and then we do maximum likelihood inference to transcribe.
I see. Okay.
Yeah. There's no supervision, and we're training and testing on the same document because it's totally unsupervised. Because we have to learn the font in that document before we can transcribe. Yeah.
And 1 page is enough to learn, or is it like a...
1 page turns out to be enough, yeah. So ideally, we'd be able to do this on whole books and actually update the language model parameters as well. But right now, it's a little slow. But we're working on making it faster. So I want you to see in this example, in the predicted typesetting, that we're capturing the wandering baseline. The model's using the vertical offset random variables to do that, which is good. The model's also using the inking random variables to capture the over-inked H on the left and the under-inked E in the word the. So it's cool to see that the model is kind of doing what we intended it to do. I want to show you another example. This snippet reads, taken ill and taken away, I remember. And again, we use EM to learn parameters from the whole page that this snippet came from. And we get a transcription, and it turns out, again, we're right in this case. And then here's the predicted typesetting. And so here, I want you to see that, again, we're modeling the wandering baseline. This is something I mentioned earlier. The wandering baseline in the input here isn't a result of the printing press and how it worked. This is actually a result of 3-dimensional warping as you get near the binding of a book. And so we can capture that. But what's more cool is that because the page begins to face slightly away from the camera as it recedes in 3-dimensional space, those characters are actually thinner. And so because we can generate glyphs of different width, we capture that here with the thinner B, E, and R. So it's kind of cool that we can capture this effect, because these effects are kind of common in a lot of these historical documents.
So just to make sure, so the baseline can actually be not horizontal?
No, so we don't model the fact that they have slanted. It's an approximation where we're saying, yes, they're kind of moving down and getting thinner. It's like,
Yeah. Baseline is just
baseline doesn't have an angle. It's just an offset.
Because the red dot you show in the previous slide, they are sort of...
Yeah, that was just, I'm just like laser pointering with the lines. Okay, so now let me talk about actual real experiments. I'll show you results on 2 different test sets. The first was taken from this Old Bailey corpus that I talked about earlier, the Old Bailey Courthouse in London. And here we chose 20 images at random, distributed across years, each consisting of 30 lines. And that formed our test set. And we manually transcribe these guys to get the gold data. And the second test set comes from a corpus called Trove. And so this is a collection of historical newspapers from Australia that's curated by the National Library of Australia. And here we took 10 images at random, again, each consisting of 30 lines. Well, we compare against 2 different baselines. The first is Google Tesseract, which I mentioned earlier. The second is a state-of-the-art commercial system called Abbey FineReader. And this is actually the system that was chosen by the National Library of Australia to automatically transcribe the documents they had in Trove. I'll show you experiments with 2 different language models. The first is out of domain, as I mentioned. This we trained on 34 million words from the New York Times portion of GigaWord. And the second language model is in domain for our data set. And this came from manually transcribed text from the Old Bailey corpus, 32 million words.
Is there any particular reason you restricted it to just the New York Times portion of that GigaWord? Or?
Yeah, so it's a character 6-gram model, and it seemed like more data wasn't helping, and it was making reading stuff in slower, but yeah. Okay, so I'll show you results in terms of word error rate on the first test set, which was the Old Bailey corpus. So here, bigger bars are worse. So Google Tesseract on this test set gets a word error rate of 54.8, so it's pretty bad. It's kind of like we saw in that small example. This is getting more than half of words wrong. Abby Fine Reader does a bit better. It gets a word error rate of 40 on this test set. And our system with the out-of-domain language model gets a word error rate of 28.1. And with the in-domain language model gets a word error rate of 24.1. So that's a pretty big reduction in error. It's actually more than a 50% error reduction compared to Google Tesseract on this test set. Here's the second test set, Trove. Here, Google Tesseract's doing even worse. This is kind of a harder test set in a way. It's getting a word error rate of 59.3. Now, Abby Fine Reader's getting almost half of words wrong, 49.2. And our system with the out-of-domain language model is getting a word error rate of 33. And so that's not quite a 50% error reduction compared to Google Tesseract, but it's kind of close. Okay, so I just want to go back to the original example and, sorry.
You didn't show the result using the other language model here, why?
We never ran it. We could have. We figured that it would have been more in domain than NYT was for Trove, but not as in domain as it was for Old Bailey because it was actually for the Old Bailey corpus.
Would it make sense to use character error rate here?
Yeah, we have those numbers too in the paper. We went back and forth about what to present. The character error rates are much lower, and that's what people usually present, but they're kind of misleading because once you get a couple characters wrong in a word, it makes it hard to search for, makes it hard to read. I don't know. I think it's better to see word error rates. But I think the character error rates are in the tens, something like this. I don't totally remember.
Is there a reason people don't use word language models? Like you're using a 6-letter term?
6-gram, yeah.
Sorry, a letter, right?
Yeah, character, yeah.
Yeah. Why don't people use words?
So we did a lot of experiments actually after we published the paper on trying to boost the language model because we thought, like you did, less ambiguity is better. It's actually hard. The problem is that your state space in the semi-Markov model gets huge. And so you have to do different approximations. We started doing beaming. And the beaming kind of interacts badly with models that have these kind of 2 levels of generating words and then characters we found. And even when we waited long enough to get more exact results, we saw that it wasn't giving a big improvement for the out-of-domain language model. Even for the in-domain language model, it wasn't giving huge improvements. Which is we're not totally sure. We expected it to give bigger improvements, but it didn't. So here's that original example again. So just to give you an idea of how legibility gets better. This is Google Tesseract with more than half of words wrong. And this is our system with fewer than a third of words wrong. This is our output on that document. You can see that it's easier to read. Okay. Next, I just want to show you some examples of the fonts that we actually learn. So first, here is the initializer for the glyph shape parameters that we use for the character G. And you can see that it is a mixture of a bunch of modern fonts. There are kind of 2 different types of dominant Gs that are visible here. The first is the type of G that has the descender starting on the left. And the second is the type of G that has the descender starting on the right. So here are the final parameters that we learned for these glyph shape parameters after running EM on various documents from across different years. And you can see that in all of these historical documents, the type of G with the descender on the left is used. and we were able to learn that. We were also able to learn more fine-grained distinctions in glyph shape as glyph shape varies from document to document and across years. There's one more cool thing that we can do with our model that I want to talk about, and this has to do with the fact that we're actually generating all the way down to the level of pixels. We can treat obscured pixels in the input as either that are a result of over-inking or blotched ink or even tearing in the page. We can treat obscured pixels as unobserved random variables in the model, and then during learning we can marginalize them out, and during transcription and inference we can actually make predictions about their values. So here is a portion of a document that we found that had severe bleeding ink from the facing page. You can see that here it's these big capital letters that got superimposed. We went and manually annotated that bleeding ink in red, and that's why it's red here. We told the model during learning to treat all the red pixels as unobserved, and during inference to try to fill them in. And so here's the predicted typesetting that we get on this portion. You can see that we correctly identified the word mouth, which is cool, and we made reasonable predictions about what pixels should go there. We also correctly identified the missing D that was totally obscured in the word found, and again made a reasonable prediction of what the D shape should be that goes here, because after all we know what D's look like in this document because we learned the font on this document. So that's cool, and we're looking at there's future applications that you could think of doing, integrating this model with different kinds of reconstruction techniques that we're looking at. Okay, so now I'll conclude. So unsupervised font learning, we've seen that it can yield state-of-the-art results on documents where the font's unknown. We've also seen that generatively modeling these sources of noise that were specific to the printing press era documents was really effective. And finally, we're trying to make this into a tool so that historians and researchers can actually use it. And we're working on that now. The biggest problem is that it's slow right now. We're trying to make it fast. And thanks. Yeah.
So one observation a few slides back when you showed, a comparison of the Google recognition and your recognition.
This one?
Yeah.
Yeah.
Exactly. And so when I look at it, it looks like, especially names.
Yes. So this is why we're thinking of adapting the language model. So these are like court transcripts. So it's almost like a script. The names occur over and over again, and we'll transcribe the same name completely differently every time we see it. I do want to I think that this is funny. If you see what Google Tesseract did, fool morphs. I just want to point that out. I think it's funny that it said that. But yeah, so some kind of constraint. We thought a little bit about this, so that you don't transcribe the same name differently each time. If you added that constraint, that might improve things. Or if you simply try to adapt the language model.
Yeah, maybe a naive thought, but I was thinking if you had a separate character engram model for capitalized.
That's a good idea, yeah.
Things, because the names are often, they may not be English, they may be coming in from other languages. There's a lot of character engram probabilities that are probably very different in names than they are in English in general.
That makes a lot of sense. And sometimes, especially if the name isn't severely degraded, you'd be better off ignoring the language model altogether, maybe. Like, for example, you can see here, this looks like the language model likes it, but it probably doesn't, the pixels don't like it. So it's a good idea.
So I know this is probably a weird question, but did you try your model on the modern document?
Yeah, we did, and just a little bit. And it does, the character error rates on modern documents in our system and other systems are tiny. It's less than 2% character error rate, 1% character error rate. And so it seemed like ours was about as good as Google Tesseract. The thing is, ours is so much slower than Google Tesseract that you should just run Google Tesseract if you have a modern document.
So how slow it is right now?
Right now it's about 10 minutes per page, maybe 20 minutes. And that's on a pretty fast desktop. It turns out actually the biggest bottleneck isn't the dynamic program, which we've made really fast now. The bottleneck is actually the computation of all the emission probabilities for all the different spans, because there's actually many different types of templates you could actually use to print things. You have all different widths, different offsets, different inking levels. They're parameterized in a really simple way, but you actually have to compute how each of those possible templates would fit with the input. And so that's a big computation. You can write it as something that looks basically like a matrix outer product. And so just doing that in our code made it faster, having to do with like cache locality and stuff. But we're also looking at putting it on a GPU because it's sort of ideally suited for a GPU. But that said, we're worried that historians or humanities researchers aren't going to have like some desktop, some gaming desktop with like 3 GPUs in it. So we're also looking at approximations that you could do to speed it up on the CPU.
So this is sort of a question related to Michael's, but it strikes me like your word error rate is much bigger than the character error rate, which seems like I don't have any concrete idea, but seems like there is some sort of error correcting you could do if you, maybe also related to Patrick's question too, is like if you have some word-based kind of language model,
right,
and you actually try to recover from the characters, like maybe your whole word just missed a couple characters.
Yeah.
And can you sort of correct that?
Yeah, if we could spit out some kind of lattice and then rescore it with some high engram word, something like that. Yeah, that's probably a good idea. People do a lot of post-processing, and I think they see improvements in OCR outputs.
So for the Google tool, or for the other tool, did you get the score of each characters? So you only get the output, right? You didn't get the score. What's the second most possible character of this?
Yeah, no, we didn't look. You mean like in best lists or something like this?
Yeah.
Yeah, we didn't try that.
I was wondering if you have that and you just smooth with language model, probably you would do pretty well.
Yeah. Yeah, that's possible, yeah. It's a good idea.
So you're not planning to sell your tool as the other ones are commercially available?
Yeah, we don't. I don't know. Not really.
So one question, sorry. How is it possible that people transcribe 32 million?
Yeah, I don't know. It's pretty amazing. They said it's like one of these. It's not paid, I think. They set up a website and people come to the website and they think it's fun and they do it, and they got lucky that enough people got interested that they did it. Yeah. Yeah, it's kind of amazing.
So have you talked to some potential consumers like
Australia government?
Yeah, we should call it.
No, I'm thinking of more about like the social scientists.
Yeah, so we've been in contact with somebody at Berkeley, yeah. And we're trying to figure out so we looked at their documents and they do look a lot like these documents. And so really now it's a matter of us making it fast enough and making the interface easily usable for them.
So another thing you sort of gloss around, but it definitely seemed like a much better idea. It definitely seemed like a good idea that when you try to, let's say you try to learn a whole book, and you keep updating your language model.
Yeah.
You treat language model as sort of like you initialize from the general.
Right.
But then they can get adaptive from whatever preliminary result you got. So,
Yeah.
So what's the bottleneck to do that?
Well, so we could have tried it, but we figured that because we're training on single pages, that's not enough data to actually get signal in the language model. We might be wrong. Maybe you could get something like names because they do repeat. But we figured we need it to be fast enough that we can train on larger portions at a time.
So you also mentioned cost of fine. So is it cost of fine in terms of different resolution? Or?
So the course defined was that's something we're looking at too, though. But no, course defined was in terms of increasing the order of the language model over time. So that makes the dynamic program pretty fast. And then you prune using the lower order one, and we use max marginals.
It seems like in vision they are naturally.
I know, yeah, and so this is one of the approximations we're thinking about. There's an older literature on something called document image decoding, and this is also this old school kind of generative model that's similar to this, in that they're treating OCR as a noisy channel model, and they came up with some interesting algorithms with Minka back in the day, something called iterated complete paths, where you find all those emission probabilities I talked about, which are so slow for us to compute. you compute them all at a lower resolution or with some sort of like column projection to give you an upper bound on the actual probabilities. And then you find the Viterbi path, and then you update all the guys on that Viterbi path with the exact scores, and then you recompute the Viterbi path. And so once that converges, you're guaranteed that you found the right path, but you haven't had to actually compute all those emission probabilities. And so that's a place where the kind of course-defined pixel level stuff could be really useful. Sorry.
Okay, so
Big silence.
have you looked at what happens with EM iterations, like if you just did without updating the parameters, just from the initialization point?
So what's the score of the initializer?
Like
Yeah, it's like 10 WR worse, maybe more than that. So it's not totally failing, but it's pretty bad. It's like maybe as bad as Abby Fine Reader.
Google?
Better than Google, yeah.
Probably due to the joint decoding.
And the ability to model the noise, yeah. I think the joint and then the ability to do baseline stuff.
So here's a question. I'm wondering why you didn't ask this one. But so it seems, once you have a model that is this flexible to deal with noise, right? I mean, the next frontier would be handwriting.
Yeah.
And I mean, there's obviously a huge, demand for that in the biomedical domain, right?
So we thought about this, and the reason we haven't actually done experiments is we suspect it's unlikely to work because we've noticed in error analysis that the places where our model fails are where you have a large region where there isn't any single column of white space between characters. Right? So then it's on the first pass of EM, you get the segmentation wrong, and then the learning all goes wrong. You can get away with this happening where a couple characters bleed together, but with something like handwriting or cursive, yeah, or even Arabic OCR, even digitally typeset Arabic, this could be a big problem. So, I mean, it might work when we've thought about ways to, maybe with enough random restarts, like you could start to, do better, but in our initial experiments, we weren't hopeful.
So let's thank Taylor again.
Thanks.